So far we've looked at three types of intermolecular forces in Chapter 11. Let's review them quick. The first is called London Dispersion Forces, or just dispersion forces, and those happen in everything, and they happen because there is an electron interaction due to instantaneous polarization throughout the molecule. So at one instant or at 1 second in time, there might be a buildup of electrons in one area and a lack of electrons in another, giving rise to a dipole, or a positive and a negative area. The second kind are called Dipole-Dipole Forces, and these happen in molecules that are polar. So there's more of a positive area here, more of a negative area here, and the positive, of course, attracts to the negative. These only happen in polar molecules. Remember, dispersion happens in everything. Lastly is a special type of dipole-dipole interaction that happens when there is a hydrogen in the molecule attached to a fluorine, oxygen, or nitrogen. These are called hydrogen bonds, or hydrogen forces. This happens because the hydrogen nucleus is very exposed when the electron is attracted to one of these highly electronegative elements. For example, in ammonia right here, you can see that the electron from hydrogen is pulled very close to nitrogen, making it very positive over here in this part, this part, and this part of the molecule. And then that could attract to another hydrogen bonding possible molecule like water, because water, of course, will pull electrons towards the oxygen area, giving it a very negative area. And this is a fairly strong interaction. And so if you were looking at them just in terms of strength by themselves, not as a coordinated group, dispersion would be the weakest, dipole-dipole would be a little bit stronger, and hydrogen bonding or hydrogen forces would be the strongest. But remember, you'd never see dipole-dipole and hydrogen bonding by themselves. They'll always be in conjunction with dispersion forces. So we'll look at those various strengths again in just a second. One of the interesting consequences of this hydrogen bonding is actually due with liquid water. And on page 451 of the 13th edition, you can see that one remarkable consequence of hydrogen bonding is seen in the densities of ice and liquid water. In most substances, the molecules in the solid are more densely packed than those in the liquid, making the solid phase denser than the liquid phase. By contrast, the density of ice is 0.917 grams per milliliter, and it's less than that of liquid water at approximately 1 gram per milliliter. So ice floats on water. The density of ice can be understood in terms of hydrogen bonding. In ice, the water molecules assume the ordered open arrangement as shown in figure 11.11. You can see right here, you can see this open arrangement of hydrogen bonded water molecules together, and there's actually like empty space in these areas right here. That empty space gives you a larger volume per unit mass, and therefore makes it be less dense. So we're kind of lucky that way here in Minnesota, because we have, of course, ice lots of times of the year, and if it wouldn't float on top of liquid water, we'd have lots of lakes and animals inside of lakes that would be very much in trouble. All right, there's one other type of force that we need to address before we move on from these, and this is a special kind of force that happens between ions and dipole molecules. This is called the ion-dipole force. An ion-dipole force happens between a polar molecule and an ion. Remember, an ion is something that is positive or negative, and then the polar molecule, of course, is something that has a positive end and a negative end to it. And so these positives and negatives attract to one another. One of the more popular places that this takes place is in solutions. Solutions of water are very possible. And then ionic compounds, things with positives and negatives, are surrounded by these positive and negative water molecules. And so you can see here in the textbook, it even looks better than my picture, that the Na positive ion from sodium chloride would be surrounded by the oxygens, the negative part of the water molecule. And then the chlorines, Cl minuses of like sodium chloride, would be surrounded by the positive ends of the hydrogen. The exposed nuclei of the hydrogen right here would be very positive and then attracted to the negative part. This can be a strong interaction, and it is especially important for solutions of ionic substances in polar liquids. So knowing these four different types of forces now, it's important to be able to compare these intermolecular forces in terms of type and in terms of energy. So Here's a chart that we're going to put together, and it's comparing intermolecular forces. And on this side, we're going to write down the types of the forces, and over here we'll give an approximate amount of their energy for each type of force. And if you want to kind of follow along with this, it's on your textbook. Let's see, that'd be page 253, kind of towards the bottom. And I kind of condensed this chart right here to a left-right version versus a top-down one like this. So you can see that London dispersion forces, or just dispersion forces, account for an energy between 0.1 and 30 kilojoules per mole. Their very strongest would be really large molecules with lots and lots of electrons. The weakest ones, of course, would just be between like single atoms, like neon or argon or something like that, because those wouldn't have very many electrons and wouldn't stick together very good, and therefore their energy would not be very strong. So it happens in all types of things, and it happens because there's instantaneous dipoles. And here's one example, a methane molecule to a methane molecule, both nonpolar. The only force inside there is dispersion forces. Remember that these dispersion forces occur in all things, and so everything has these forces, even if they have dipole-dipole forces, and even if they have hydrogen bonding forces, they also have the London dispersion forces. The second type are called dipole-dipole forces, and remember these happen in molecules where there's a positive part and a negative part, and these are between 2 and 15 kilojoules per mole. So you can see not overall, they don't eventually get as strong as London dispersion forces, but remember these happen in conjunction, and so even if a molecule has dipole-dipole forces, it also has London dispersion forces. Here's an example of HBr, and so the negative part of the Br right here would be attracted to the positive part of the HBr over here. All right, the third kind are the hydrogen bonding, or the hydrogen forces. And remember, these kinds have to have an H connected to an FO or N. These are between 10 and 40 kilojoules per mole, so they can be very strong in comparison to the other two types of intermolecular forces. And so if you had NH3 molecule right here attracted to another NH3 molecule right here, those would be held together by hydrogen bonding. But remember, they would also have dispersion forces. Now, the bigger the molecule, meaning the more electrons that it has, the more dispersion forces take precedence. But if they're a small molecule like this, nitrogen's not a very big atom, hydrogen's not a very big atom, hydrogen bonding is the thing that holds that together. Water's a perfect example of that. Hydrogen bonding is the main thing that holds that together. The next are ion dipole that we just learned about. These happen between ions and polar molecules, and we used water in sodium chloride as an example of that. Sodiums are, of course, attracted to the oxygen part of the polarized water molecule. Chlorides are attracted to the hydrogen portion of the water molecule. These are greater than 50 kilojoules per mole. These are very strong. That's what allows us to have things dissolve in water and then break up into their ions. All right, just for comparison, now this is not an intermolecular force, but this is an intramolecular force. A covalent bond. A covalent bond would be between like carbon and hydrogen, or between a hydrogen and a bromine inside of this molecule, or between a nitrogen and a hydrogen. This OH bond right here would be a covalent bond. So they're actually an intramolecular force. But the only reason I put it on here is to give the numerical value. These are 300 plus kilojoules per mole. And so you can see that these bonds right in here, these covalent bonds, are much stronger than any type of these intermolecular force interactions right here. So stronger than the intermolecular forces are the intramolecular forces that hold the actual molecules together. That's why when you boil something, or when you melt something, or when you heat something up, you don't break these bonds. You don't break the OH bonds right here. You break the attractions between the molecules, the intermolecular forces. And then lastly, ionic bonds, another good one to compare it to. These are greater than 150 kilojoules per mole, depending on what the ions are that are stuck together. So let's practically put a couple of these to some problems. Let's take a look at sample exercise 11.2. This one says, list the substances, and then it gives BaCl2, hydrogen, carbon monoxide, hydrogen fluoride, and neon in order of increasing boiling point. Let's see if we can get that to show up just a little bit better. Maybe if I switch the paper. There we go. That'll probably help. So the substances I took from right here, from this sample exercise, and I listed them right up here. And then what it wants us to do is list them in increasing boiling point. And to be able to know which ones are going to stick together the best and then therefore boil at the highest temperature, we need to know what are the intermolecular forces that hold each one of these species together. So let's just go left to right and we'll talk about what kind they are. So BaCl2, Ba and Cl's are going to be held together right here by what's called an ionic bond. How do I know that that's an ionic bond? Well, because barium's a metal and chlorine's a nonmetal, and metals and nonmetals come together and make ionic bonds. They have an electron stolen by the chlorine right here, and then we have a Ba+2, and then we have two chloride ions right here. And as we just looked at right here in our little chart, ionic bonds, well, they have a really, really strong interaction, 150 kilojoules per mole or more. And this one, I would argue, would be even more than that, because remember, it's governed by lattice energy, and lattice energy, remember, is equal to Q1Q2 divided by D, and the larger the Q is, the larger the lattice energy, and we got a +2 right here going on the top. So this one is probably going to be our highest boiling point to start with right away, because it is super strongly held together by ionic bonds. But let's keep that in mind and just write it down. This is going to be ionic. The next one, H2. What holds H2s to other H2s? Well, if you draw the Lewis electron dot structure for it, hydrogen is held together by hydrogens just by a covalent bond because they're both nonmetals. But then what holds or causes hydrogen to attach to another hydrogen molecule? Well, this interaction, you only got one choice. It's going to be dispersion forces, right? Because this happens to be a nonpolar molecule and a nonpolar molecule, so we only have London dispersion forces in this one, and there's very few electrons, so this would probably be our lowest boiling point. We'd probably want to go into gaseous phase right away because these interactions are not very strong. Next we have carbon monoxide, and if we draw this one, it would be carbon with a triple bond to oxygen like this, and then if it saw another carbon monoxide molecule, then this molecule, this two nonmetals stuck together, would be attracted to this two nonmetals stuck together by this little dashed line right here. Carbon and oxygen are a positive and negative polar molecule, and a positive and a negative right here, and so we would have not only dispersion forces, but we would also have some dipole-dipole forces helping hold it together. So we'd have two different types of forces going here, LDFs and dipole-dipoles. So we'd get some energy from that, some energy from this, and it would probably stick together definitely better than hydrogen. Probably not as good as an ionic bond, but pretty good. All right, HF, hydrogen is connected to fluorine. Ooh, remember when hydrogen is connected to an FO or N, we have a special kind of interaction between molecules. Because remember, the hydrogen's nucleus is very exposed and very positive, and then that would cause fluorine to be very negative because it would pull the electron close to itself, and then this positive part of the hydrogen in the molecule would be attracted to the fluorine molecule very strongly right here, and we would not only have London dispersion forces, but we would have hydrogen bonds. And remember, hydrogen bonds are the strongest one right here. I mean, we can be up to 40 kilojoules per mole of attraction right here. I know we don't have that many electrons, so we wouldn't get a lot from London dispersion forces because those aren't very big atoms, but you would get some. And then lastly, we have neon, and neon is just, well, neon. I mean, if you draw the noble gas, it's just neon like this. What sticks one neon to another neon? Well, there's only one choice, and that would be London dispersion forces, right? London dispersion forces are based only on electrons, right? The more electrons you have, the stronger they're going to stick together. So let's start from the wimpiest holders togethers here, the lowest boiling point. So we have only London dispersion forces here and only London dispersion forces here. So what's the deciding factor between those two? Number of electrons. Who's got more electrons? Well, hydrogen would have 2 electrons. Neon, I believe, would have 10 electrons each. So hydrogen wins. Hydrogen would be the smallest or the lowest boiling point. And so then neon would be just a little bit bigger than it, a little bit higher boiling point because it has a few more electrons, 8 more to be correct. All right, then our next choice would be between our London dispersion forces and dipole-dipole containing 1 and our one that has London dispersion forces and hydrogen bonding 1. Well, as we knew before, hydrogen bond can contribute significantly to the energies that hold it together, and so carbon monoxide would win that one and be the one that would have the next highest boiling point. Then HF would be our one with the higher boiling point yet, and then lastly would be our BaCl2, that is the highest boiling point one of all, because it is ionically held together by two, a positive and a negative Ba and Cl, and we know that ionic bonds are